Hello everyone, welcome to Civil Softwares. Today we are studying Gaussian point integration system and we are going to solve one complete question as well. So let's say we have a geometric space with coordinate x and it is plotted against some function fx. That function can be of any degree. And let's say when we plot x and fx, we get the curve like in the left hand side. This one. Let's say this is the curve first. Then the main point about integration is finding the area under the curve. For example, let's say we want to find area under this curve from point A. Let's say, so this is A to point B. Let's say we are interested in finding the area under this domain. Okay, then our traditional way would be to do it directly. For example, integration value, which is equals to the area under curve, is given by integration from point A to point B and then fx dx. If you do this, then you're going to find this area, right? It is going to give us this area. But under Gaussian point integration system, we do things a little bit differently. Now, what we say in Gaussian point integration system is that, for example, let's take the same curve. Okay, let's take the same curve roughly. This is fx, this is x, and here we are trying to find the area under the curve from point A to point B, but using Gaussian point integration system. For now, just keep in mind that Gaussian point integration system is the approximation system. It approximates the area under the curve. How does it do it? So Gaussian point integration says that, okay, under this curve, let's take some arbitrary points. For example, let's take 2 points under this curve. Let's say this is point A, point first. A is already given to this one. So let's say this is x1. Okay, this is x1. Let's say this is x2, which are 2 points we took in between A and B. Now, with the help of these 2 points, we are going to approximate the area under this curve. And for this explanation, I chose 2 points. The first point is here and the second is here. So we have x1 and x2 and corresponding functional values. We can say this is fx1 and this is fx2, right? This one and this one. So now, how can we get the area? So alternatively, the same area can be found out by using the sum of these functions, but by multiplying it with certain weight factor. This is w1 times fx1 plus w2 times fx2, and these w1 and w2, these are just the weight multiplier. These are weight multiplier so that we can approximate to the total area. Okay, here I chose two Gaussian points, so we only used W1 and W2. But for example, we have multiple. For example, we have multiple Gaussian points. Then what would the formula be? So the formula would be integration equals to summation of I ranging from 1 to number of Gaussian points that we have, and with each corresponding weight factor, and fx for now. Okay, for now. So fxi. Okay, so this is the formula. But easier idea would be that, okay, this function, any function fx could be anything. So it would be a very nice idea to map the function fx to a universal system. So what does mapping do? Okay, what does mapping do? Let's say, okay, now here comes the play of mapping. So what we are converting is, so since fx function can range from a to b, and a to b can be anything, so we make a standardized form of local coordinate xi, in which every function will be mapped from the range -1 to +1, and this is the main technique. And for this system we have certain predefined weights which we can directly use to find the integration value. So here I have tried to show that this function fx, now we are going to change to function of xi, and this range of x we are going to change to xi, which will be ranging from -1 to +1. So now whatever we had before, a to b would be converted into -1. So this is xi1 equals to -1 to xi2 equals to +1. So we just changed the range a to b to -1 to +1, and this function will no longer be fx, but this would be fxi. Now, under this circumstance, we are going to select the Gaussian points. For example, let's say we have multiple Gaussian points. For example, let's say we have 3 Gaussian points. Then we take, okay, let's say this is the first Gaussian point, this is the second Gaussian point, this is the third Gaussian point. Okay, so this is xi1, this is xi2, this is xi3. So for this example, we have xi1, xi2, xi3. We have 3 Gaussian points. You may have already made a guess that more the number of Gaussian points, the more accuracy. So under this system of converting fx to fxi, we have certain formulas that you need to know. Now, what is our main goal? Our main goal is to convert this a to b fx dx integration into xi-1 to xi+1 f of xi, and we have determinant of Jacobian times dxi. Okay, determinant times dxi. This is determinant of Jacobian times dxi. This is our main goal, where where what is the relationship between x and xi? It is something like this, not something like this, exactly this, 1 by 2 of a 1 minus xi plus 1 upon 2 b 1 plus xi, where a and b are the ranges from the original integration as shown in the left figure, and xi is the particular point of interest, which for now just know this. When we do the numerical, you are going to be very clear about what we talked about in this video. So this is first formula, and you may have noticed there is something called determinant of Jacobian. Determinant of Jacobian is nothing but the partial derivative of dx upon dxi. So if you do partial derivative of x with respect to xi, you are simply going to get half of b minus a. Okay, so this is the technique which you use for determining the integration value. So here is the summary of the formulas that we use for different Gauss points integration. For example, let's look at this one Gauss point. For example, we have to, find the area between 2 points. We mapped it under xi equals to -1 to +1. And now, for example, we chose only one Gauss point. Then our formula would be to find out the functional value for xi equals to 0 and then multiply with 2. So this 2 is the weight for 1-point Gaussian integration. Similarly, if we use 2 points, this is point 1 and this is point 2. Now you may have realized that this is the coordinate xi equals to 0, as this is -1 and +1. This is the middle point, and here also xi equals to 0. So the first xi1 would be here -1/√3, which is basically just this point, -1/√3. And then this xi2 would be +1/√3. Then what is the value of weights here? So as you can see, the value of weight is 1. Here also the value of weight is 1. So weight value are just 1 each. Okay. Similarly, if we use the 3 Gaussian point, as you can see here, xi2 is 0. This is the first Gaussian point. This is the second Gaussian point. This is the third Gaussian point. And the first Gaussian point would be -√3/5, which is this xi1. So this 0 is this one. And then +√3/5 is xi3. And these are its weight. Weight 1, weight 2, and weight 3. Just solve this and then you're going to get the integration value, which is basically the area under this all curves. So here I'm going to tell one more thing. So there is a formula to determine how many Gaussian points you use, and the formula is like this. So degree of polynomial function is less than equals to n minus 1 ng, where ng is number of Gauss points, and degree of polynomial is just the degree of certain function. So let's say, for example, we have a function fx equals to 2x squared plus 3x minus 1. Okay, now what is the degree of polynomial? Degree of polynomial is 2. then how many Gauss points would we use? So 2 is less than equals to 2 times number of Gaussian points minus 1. So it's 3 less than equals to 2 number of Gaussian points. So number of Gaussian points would be greater than equals to 1.5. So we take it nearly equals to 2. So take 2 Gaussian points and so on. So if degree is 3, find the Gaussian point, degree is 4, find the Gaussian points, use the formula and find out the result. Now let's go to the numerical example. So as everyone can see, so we are given a function fx which has the curve as shown on the right hand side, and we want to find the area under the shaded portion in the graph, which is from 1 to 4. So the question says you have to find using the Gaussian integration method, but first let's check what is the integration value of this function manually. So if you just hit the calculator, or if you just calculate the value of this function minus 7x squared plus 12x minus 4 times dx, then your integration value is going to be 10.6875. Okay, so we will check our results with this value and compare if the answer we get is correct or not. Okay, now we officially begin the process. So step one, determine number of Gauss points. So what is the degree of polynomial? Degree of function fx. So the degree of function is the highest value of the variable, right? Power of the variable. So the highest of the power of the variable is 3. So its degree is 3. So d is 3, and now we have to find the number of Gauss point, right? So we just use the formula. Degree is less than equals to 2 times number of Gauss points minus 1. So our degree is 3, should be less than twice number of Gauss points minus 1. So 4 is less than equals to 2 times number of Gauss points. Therefore, you get number of Gauss point is exactly 2. So this problem is a 2.2 Gaussian point integration. Okay, 2 Gaussian point integration. But always remember that this function has to be mapped into this system where it has to range from -1 to +1. And then, for example, let's say this function looks something like this. Then this function would be f psi. So this is the mapping which allows us to convert from coordinate x functional value fx into xi and f psi. And how are we going to do it? Let's see in step number 2. Map the function fx to f psi. Okay, and how are we going to do that is using formula x equals to 1 by 2 a minus xi plus 1 by 2 b 1 plus xi, where what is the value of a? 1. What is the value of b? 4. So x equals to, what you will get is 1 by 2, value of a is 1 minus xi, value of b is 4, 1 plus xi. If you solve this, you will get x equals to 5 upon 2 plus 3 by 2 times xi. This is one relation that we will use, okay? And as you have already seen in the formula before, that we need to find something called determinant of Jacobian, which is just dx over dxi partial derivative, and we just get 3 over 2. Determinant of Jacobian is to be done when we change the coordinate system from one to the other, which we did here. So now let's move and see what we have to do now in step number 3. Now in step number 3, I would just like to recall that for getting the value of -1 plus 1 f psi d psi times determinant of Jacobian. So this is going to give us our required result. And for the 2-point Gaussian system, what we did was weight 1 times functional value -1 over root 3 plus weight 2 functional value plus 1 over root 3, which is basically this section, okay, this section. And we are going to multiply these all values with determinant of Jacobian, which is just 3 over 2. And as you remember that for the 2 Gaussian points, value of weight 1 is also 1 and weight 2 is also 1. So you just find the value of -1 over root 3 plus functional value of 1 over root 3 and then multiply with 3 over 2. But here you have to remember that this is the value of chi. This is the value of chi, which is basically I'll show you, which is basically for the 2 Gaussian points, what we are doing here is we are just converted this, and then for the 2 Gaussian points we say, okay, let's take one at -1 over root 3, and if this is 0 point, let's say this is +1 over root 3, and then we are going to multiply with weight, and then it is going to approximate the area under this curve. Okay, so remember this. Now let's see. Be careful, okay, for psi equals to -1 over root 3. Okay, here value of psi we put -1 over root 3. But if you look at the function that we are given, our function is in x. So now we find the value of x for psi is -1 by root 3. So for psi is -1 by root 3, what is the value of x? We're going to find that. Okay, as we know the formula, x equals to 5 over 2 from this section plus 3 by 2 times -1 over root 3. Then we're going to get value of the function. Let's say this is x1 is get 1.633. Okay, similarly for xi equals to +1 over root 3, you are going to get value of x as 5/2 plus 3 over 2 times positive 1 over root 3, which is eventually going to be 3.366. Okay, so now we know that fx value, what is the function that we have? It is 1.25 times x cubed minus 7 times x squared plus 12 times x minus 4, right? So first of all, just put f 1.633, which is basically fx1 for this. If you put value of x as 1.633 and hit the calculator, you're going to get 2.372. Similarly, for f 3.366, you are going to get the value 4.7530. Okay, we're going to get this now. Finally, let's find the integration value. Okay, integration value equals to the value of weight 1 was 1, and value of fx1 we got 2.372 plus weight 2 times fx2 was 4.7530. Just multiply all of this with the value of Jacobian determinant, which we got 3 over 2. If you calculate the value, you are going to get 10.6875. Okay, now you may be wondering that we said, okay, we get the integration value using the formula weight 1 f psi 1 plus weight 2 f psi 2, and then we said, okay, psi 1 is minus 1 upon root 3, psi 2 is positive 1 upon root 3, and then multiplied with the value of this weights. But why are we using fx1 and fx2 for this? Why are we again going back to x1? Because the answer is simply because we are just mapping this. We are just mapping this. The functional value is not going to change. Okay, it is not going to change, and I was also confused because here we say, okay, xi1, xi2, and then again we use the value of the functional values, because anyway it's the same, because we have the relationship between x and xi. Whether you use xi and calculate the functional value, or you convert the value of xi into x and then find the fx, it is going to be the same. So do not get confused, it's the same thing. Now from Gaussian point integration we got 10.6875. Let's see what we got using direct integration. Okay, so where did we do it? Okay, so see here, we exactly got 10.6875 here doing direct method, and here also we got 10.6875, so it's verified, it's okay. So this is basically the Gaussian integration, and you can do this for 1 point, 2 point, 3 point. The technique is the same. Thank you guys. I hope this video becomes useful to you. See you.